Here we are. Let's close this. All right. All right, guys. So yeah, there it is. All right. So as I say, guys, we're going to work with the paper and not fight the paper. And I'm saying the paper is already set. The direction of the paper is communicated in the topics, and we just have to work with it. All right. No. The reason I gave the analogy with the salmon is that it's thing I believe it's the only fish that swims upstream up the river, whereas other fish follow the flow of the river. If it flow down, the fish usually flow down, right? But the salmon swim upstream. No, it's a routine because they usually do that to spawn, either to spawn meaning reproduce, and in the process of swimming upstream now, the river against them they have to be they have to be very strong. So they at that stage of them life, them swimming upstream, they tend to want to jump through the water at various stages, and then at that stage now they are caught by bears, right? No, and that the analogy I'm trying to get you to understand with that is that when you go into an exam, you know, you're fighting the paper means that you're going there with doubtfulness, everything that will cause prevent you from reaching where you want to reach. The objective of facing the exam is to pass the exam, a few months down the line, and be happy with how you perform and move on to the next stage. Yes, so in this case now, what CXC has done, and it's a first in history they have done this. Um, they actually all right, I think maybe some persons want the link for class, so I just need to send that one. All right, so just give me a second here. Uh, yeah, there you go. I have the invite link there. Probably as well we have persons who wanna join here and join through YouTube, so we have to cater for those. So let's all right, and then there you go. So we're sending this information to the persons. All right, so and here it is. All right, so we have how much? 11 persons here today. That's good. Um, that's good. And still not seeing Antonio. Antonio should be a member of the class, but again, he's a quite a casual visitor. Um, drops in when he's feeling like it. But yes, guys, they have sent us a gift here of 18 topics. 18 topics. And I was actually looking at this before class began. And I'm actually happy in the sense that they have to some degree send the paper two, by the way. And I should highlight that this is just for paper two. So it's paper two. All right. Now, as I say, the formula for paper two is that it's 100 marks. And just like what I did for chemistry last night, this is a new side. Paper two is equal to um is equal to 6 questions. And then these 6 questions are actually divided. Question one, we have question two, question three, question 4, question 5, and we have question 6. All right, question 1 now. The biggest question is actually 25 marks here. And then this is 15. And 15 apiece here, carrying up to total of 100 marks. Now, this is the exam formula for this year. So, important to know each, well, the 6 questions now, think of them as topics that they will ask you about. And first of all, your performance on paper 2 is half of your total grade. SBA is 40. Okay, let's keep word playing here. All right, so that's really gonna be 40 marks. And of course, paper 1, what you're going to do afterwards, sometime in July, is actually equal to 60 marks. So this is outside the topics that you get is outside of these. The topics that you have won't help you with what I put in the square, you know, what a circle here. Let's see, what I've highlighted here is not the list of topics not related to it. So screw again. All right, any questions here, guys?
No, sir.
All right, so 6 lovely questions divided into 25 marks for the first one and 15 apiece for all the other questions. Also, the time that you have, the duration that you're going to get is actually 2 hours. So we put it in terminology, and it's actually going to be 2 hours and say 30 minutes. Actually 2:30 minutes. So that's going to be, well, that's going to be 9 and 6, 15, 150 minutes. That so it's going to be 150 minutes. If we check it out, it's going to be 150 minutes. 150 minutes, guys. So the time factor comes in nearer to exam. Do you want to be working with time as well? So if you're a person that's gonna work slow, then your approach will be slightly different. But we can talk more about that later on. Just want to focus on understanding what is it that you're gonna be doing. All right, so 25, 15, 15, 15, 15 is the formula. All right, we can even break this down. Let's use a different color here. What we're going to do here, we have a plan for these columns because we want to put in the topics them. In fact, we might know what topic will be in which question because we're going to use common sense here with the outline that they give us. All right, so so everybody seeing the 18 topics, right?
Yes, sir.
Yes, sir.
All right, good. No, all right, no. The reason why I like this is that one, what we're doing this year, we actually did a brave thing. We cut mechanics, we went on to temperature and gas laws. We did all of these waves and these things, reflection, refraction, critical angle, total internal reflection. We did the particles in the atom, we did radioactive emissions, we did half-life. So that's why I put a tick there. All right. And what I'm going to basically highlight is the areas that we would have covered to a large degree in class. In fact, we did there we go. In fact, we did all of this. So, and then all of this here. So we have to, we're going to revise these, but there are some topics we need to sort of have ideas about. We just started resistance last class. So we spoke about Ohm's law. So pretty much here we figured we knew that resistance would feature in every exam in one way or the other. But alternating current, we did mention this last class as well. I think we didn't know to have. Let's go back to the last class notes. We were breaking down the paper, and we're actually predicting all of this too for the topics. But then, I gave it this from last class, and I did say that AC current. This is have to focus on it. So pretty much for the exam, let me just put a circle around this and mention that this is for 2021. This is where they're going for 2021. 2021 exam will focus there. All of these things that you should know are also included there as well. So so this is it. So we did this for the lab. So all right, so forget about static electricity for paper 2. So what CXC has done is basically say, all right, don't bother study this. Of course, you might need to know some circuit symbols for yeah, we need to know some circuit symbols, but certainly with Ohm's law, not well. Let's see though. I have a plan for each of these topics anyway. So, but then this what we did in last class would be helpful here. All right, so let me see something. Okay, so the Asian is saying she having problems connecting. All right, let me just say. All right, let me see. I will send this link to her. All right, there she is. All right, so then, yeah, so I thought that. So that's it, guys. Put in the red highlights around those that we have completed. So we have 1 to 3. In fact, you have been plotting graphs anyway. So this shouldn't be new. This graph work really is the same 10 pointing. I tell you, the marking for your scale axis and all of that type of thing there. The marking for here. So you should know graph work, basic graph work. This is something that we have been doing. The only thing here now, so we have 2, 3, 11 to 15. Those would be relatively new to you. At least those who I'm teaching since September. That's the only new thing we're going to talk about. All right. All right, hold on a sec. Just a second. All right, so yeah, sorry about that. So versions look like they should never run out of data. All right. So guys, let me show you what deformation and turning forces is all about. So look at this today. All right, so aside from the exam dynamics here. So this is is it the most recent? Well, yeah, this is the most recent question on deformation. And I'm gonna put deformation here. And Hooke's law, because a lot of students don't know that deformation is the same thing as Hooke's law. All right, so if I was to ask who would know about deformation, maybe persons would say they don't know. But then if I ask you about Hooke's law, you say yes, you know that. But they're the same thing. So if you know one, you know the other. So anyway, Hooke's law defamation question. This was sent back in 2013, by the way. All right, and as you can see here, it has to do with, well, load and length here. But let's read through the question and see if we can make some sense of it. All right, everybody able to see it?
Yes, sir.
All right. So now, did you get a table and it shows the results obtained by a student who performs an experiment to investigate how the length of a spring varies with the load applied. All right, so when align length and the load applied. Two keywords there. We're not ready to use these words yet because, well, there's a table. And all right, so we know that this part is load and then this part is length. So this graph, right, you should understand here that as each load is added, the length is changing. So so here when a person put 2 newtons of a load. Now let me show you what the setup for this would look like. Just in case they ask you for apparatus, it could go that direction for your exam. But what does a Hooke's law lab look like? So that's something that we should have done but didn't get the chance to do it. Would normally do it in a face-to-face situation, but and if I'd known these topics earlier, I would have probably done that as well. But anyway, tell it and never still. So let's just go into this now, and I want you guys to see what's happening here. All right, so guys, this is what the lab would look like. Everybody seeing this?
Yes, sir.
All right, so so what it is then is that you add weights to a spring and you measure the change in length of the spring when you add weights to it. So the more weights you add on is the more the spring is stretched. But you understand that?
Yes, sir.
Right. So and so this is actually Hooke's law. And it's Hooke's law experiment. No, not only that, when you collect your results, when you write them down and you put it in a table, you're going to plot a graph, and the graph going to stay like this. So this is the extension. And this is your load or your force. As load and force is the same thing. All right. So this is actually Hooke's law experiment. So this is the graph, and this is the apparatus. So that's it. All right. So when you plot the graph now for a CXC point of view now, you're going to get a straight line actually. This part here, part of the graph is straight, but the last part of the graph is going to have a little tail here. But in exam situation for this, usually they'll ask you to find the gradient. This is what you call in fact, yeah, it's this thing taking a long time to respond. This part here is this is actually a straight line portion. And the thing about this is that Hooke's law is obeyed. Let me just probably save this because I don't like how this thing is behaving. I'm gonna probably save it as today's date. Today is the 11th of May. All right, so we save that now. and it's saved. Nice, hopefully. I think a lot of programs are open here. Let's close that one. All right, so guess what? Hooke's law is obeyed. All right, so this is the Hooke's law graph, guys. It's straight line up to the point where it start bend. The part where it start bend now is where Hooke's law is disobeyed. And so and right here, all right, this thing is taking such a long time to respond on. All right. This all right, this part here is the, in fact, it's a limit. As a matter of fact, yeah. It's really the limit of proportionality. It's slightly different from the elastic limit. In other words, object is deformed here. So after the straight line part of the graph, the object basically is going into a deformation. You know, deform mean, say, you know, if it's a spring you're stretching, for example, after this point, after it stop give you a straight line graph, the material itself will become like obviously stressed. You know, it's not gonna look like how you started to use it before. All right, so the same thing will happen, like for example, if you have a bed that you have been sleeping in for maybe 10 years, you know, and that bed had springs in it, and those springs would probably reach them limit, because as you get older, you're adding more force to the springs in the bed, and the bed has to absorb that force, and then it is actually becoming deformed in the process. So that's why some people bed sink in. All right. No, some of you probably know of that or maybe experience it. But when that happens, usually your parents would say it's time to buy a new bed or a new mattress. Right. So and that is due to deformation. It's because Hooke's law is stopped being obeyed. So when Hooke's law is not obeyed, it doesn't matter what the situation is. It could be your bed that you're sleeping. It could be muscles in your body. Maybe some of you in this class can split. Body in this class can split, like spread out them leg for you know, so that them thighs touch the ground. Can split like that. No flexible persons in the class. Interesting. All right. Well, those who exercise is the same thing. You're stretching muscles. You stretch them get bigger.
Sir, but you split, we couldn't answer when you say split.
Why?
No, sir. No, sir.
What's wrong with the split it?
Sir, man was supposed to split. That's
Right.
first of all.
No, come on, no, hey. No, I don't understand what you're saying. So you're saying that men cannot be flexible?
No, not that.
Sir, they can, but they're not
Yes, sir.
supposed to split.
No,
It's
no,
a-
man, look here, man. No. Come on. So what about the man them with the dancing then? Some man we have wire waist and all kind of movements in them dance routine, and
Sir,
them
can
foot
you hear me
over
now,
them
sir?
head. Well,
Yeah,
yeah, you know. So some man foot can go over them head back. That mean that if you can do that with your foot, you can split. But all right, fine. Maybe splitting is
Sir.
yeah.
Sir, speaking, they already just, we can't say, yeah, we can't speak, no, sir. So when we used to play ball and we exercise, we used to, stretch out the muscle them.
right, well, call it what you want to call it then, right? The thing about it is, if your muscles can do that and go back to its original state afterwards, then without tearing, by the way, that is elasticity. That is obeying Hooke's law. And what does Hooke's law state? Why is this law so important for it to be obeyed? This is the law of stretching. All right. So this is likely a question they'll ask here. So let's bring up Hooke's law. And thanks to Robert Hooke in the 18th century, we have this law to learn. So all right, if I don't see it, then I will have to
So I think the force proportional to the extension produced in a material.
well, that's just saying what it's saying, but to state the law, we're looking for we want a statement where you can get the full marks, right? So you probably would get a 1 mark for what you just say. But how would we state Hooke's law accurately so that we can get the full marks? Not seeing it here on the whole of the internet so far. Not pleased with these definitions. So of course, here it is. Although well, all right, there are many versions of the law, but all right, let's go. What could they ask for Hooke's law then? And let's look out for this question. All right, Hooke's law. Yeah, it states that within the elastic limits, and that's why we show that on the graph, within the elastic limits of a material, right, so the force applied to it or load applied to it is directly proportional to the extension of the material. That's it. All right, that's that's well, I would say that's a long version of the law. But it's a 2 mark. It's a 2 mark law if they ask you about it. So you must say within the elastic limits, and you must say force or load is applied to, is directly proportional to the extension of the material. Any questions there?
No, sir.
No, sir.
All right. So and remember that when I ask if there are any questions, I'm also asking if there's anything that you don't understand as well. So that applies to everybody, including those silent persons or those persons who might just get up and leave the screen or the device. But so this is it, guys. We are going for marks here. Potentially 2 marks is available for knowing Hooke's law. All right. Guess what? There are many ways to get this 2 marks, but this is the long version, more popular version of Hooke's law. What if somebody would, well, and I'm pretty sure, especially those persons at Campion and the staff schools, maybe even Manchester too, you might have a couple of youth there pushing the bar a bit, but they would say, we could say that strain, there's a term known as strain and stress, really. So strain is directly proportional to, well, let's actually put it the other room. Stress is directly proportional to strain. And let's put the stress there and the strain. So, and what I've done here is find use a sign there. This sign here means directly proportional to. So if I write this sign, I don't have to write out directly proportional to. All right, as a matter of fact, let's this spelling correct here because missed out a few letters here. Right. So that's a 9. Directly. All right. So that's what this sign mean. So everybody get that?
Yes, sir.
Yes, sir.
All right. So I don't want, so these 3 words that I write in here can be replaced by the sign that look like this. So if I write this on exam and put within elastic limits, I'll get 2 marks for stating Hooke's law if they ask that question. All right. So that's it. Or other way we can get the full marks here. We could go ahead and say force directly proportional to extension, which is close to the version that Benito was hinting at. Also within elastic limits. This is where you get the second mark. You have to say within elastic limits because every material have a limit to where it can behave elastically or elastically, if that's the adverbial term there. So this is it. Any one of this, you can state it in words or you can state it shorthand like this, and you get the same amount of marks. There is even another way you can state this. I can go again and say F is proportional to X. Because there's a formula for Hooke's law which says F is equal to KX. So that is acceptable as well. F is proportional to X within elastic limits. All right. Again, this is our plan to answer the question if they ask us to state Hooke's law. Is that clear to everybody?
Yes, sir.
All right. 4 ways in which you can get 2 marks is here, are shown here. All right. Now, let's go back. So, all right. So, and they call it deformation because, well, you know, when them teaching you this in 4th form, it's usually in 4th form you learn this sort of stuff anyway. And you sit down in class and you and your teacher have a nice time. You get all kind of activities to stretch stuff and get an elastic band and you see how far you can stretch and then all of that type of thing. You call that deformation. Deformation is when a material is permanently stressed. All right. So that's how it works with Hooke's law here. All right. Now let's go back to the question and see if we can apply some sense to this now. So we have more load and then we should have more extension. But with these results here, something is wrong with the 35, 0.35 there. That kind of look off. Maybe that's an error. And they put an error in there, they could ask about that error as well. What type of error is it? Possibilities are endless for this question, but again, they say graph work. So I guess we shouldn't get into the well, anyway, let's just treat this as the first question for now, because there are some other possibilities. But 2 Newton give you 0.36, 4 give you 0.35, and this looks like an error. Let's put a asterisk there. And then 6 Newtons give you 0.4, so that looks good. And 8 goes up to 0.46, and 10 goes up to 0.51. So again, it seems as if when you add more load, you get more extension, except for the second one. All right, everybody seeing the results here?
Yes, please.
Yes, sir.
Yes,
All
sir.
right, very good. So, and them say here, plot and PH3 a graph of length and against load here. All right. This is something that you guys even should be doing on your own. And I would like for you to do this. As a matter of fact, I will deliberately copied this. Let's see if I can group them. Not going to allow me to group them, but I can paste it in the class. And putting it in the wrong class. There's I almost put it in the chemistry class. It should be fine in the physics class. Why is the physics class so far in my WhatsApp? Because I've not been hearing from you guys. Let's just put it in here. There it is. All right, so you should be seeing the graph paper in the group, or at least a question in the group. All right. So now let's plan this question now. You're going to plot a graph for 7 marks. All right. Remember, guys, when I was teaching a graph face to face at IPAS, I told you that you can get most of these marks without plotting the graph. They say plot a graph. Let me say plot. And plotting the graph is actually maybe 2 marks out of the 7. Maybe 3 actually out of the 7 to plot. The other 4 marks, which is most of the marks, you get for not plotting, but for setting up the graph paper. And so that's the first thing you would need to be able to do, is to set up this graph paper the right way. All right, so you see your graph paper here. And you're going to label it. Put in your axis them. People waste time, draw a line with a ruler. You guys see not marking for that. The only line they're going to mark it for is the line where you used to draw the graph after you plot the point them. So no need to waste time drawing over the edge of the line. Use a graph paper. You only have 150 minutes. You don't want to be wasting it drawing a line. Drawing perfectly straight line on an exam morning will take you probably 5 minutes or maybe 10 minutes if you're nervous or something. So you don't want to waste that time. That time can be used for other questions on the paper. So anyway, I'm going to get those 7 marks here by 1 mark at a time. Now put a 0 there. I'm going to label the axis. Now, I put the axis there to show, well, all right, so I'm beginning to label it, but what will I label it as? We go back to the graph. Anybody can guess what we're going to label it as? It says a graph of length. Oh, them tell you where. Also, length on the vertical axis. Them tell you where it is. Anything them tell you first is on the y-axis. All right, so length will go on the vertical axis or the y-axis. Same thing. So get used to CXC's terminology, or the words they use to refer to things. It might be different from what you are taught. We'll understand them language here. So I'm gonna call this, what did they say? Load. All right, length on the vertical. All right, fine. So when I put length here, and the length they give you, we have to go back to the table and see what units is the length. And as you can see here, the length is in meters. All right, so this is where you're going to get a mark, or at least a mark. You're going to put the length in meters, or you could put L/M just to give it a mark there. But let's write length to be on the safe side. This now would be our load. As them to put the load on the vertical and the horizontal axis, the load is measured in Newton. So far, you're getting 1 mark here. You label the axis. I think those 7 marks though is because it's 7 marks, they're going to probably focus more on getting the plots correct. So and so we're getting at least a mark for this. All right. We're getting a mark because we label the axis correctly with the units that they want. So that's a mark there. All right. Next thing now. What's the next thing you do?
Yes, your skill.
Yeah, you're going for the scale. And these you going to try put the numbers them now and the graph. So it can be read. All right. So it's from 2 to 10. So looking at this data here, it's from 2 to 10. And not only that, the graph that you're going to plot must take up at least 3/4 of the graph paper. So it can be, so I can like bunch up the number of them close to each other. Like as them say, it's a load them say, all right, I'm going, you know what I'm going to do, I'm going to copy the data. I'm going to copy this data and put it over. All right, that's what I'm going to do. Copy it. Can I select everything here? And it allows me to group, so I have to copy it. And I'm going to put it right so that I don't have to move in back and forth here. Here's the data. And copy that data there. All right. So the load now, this going to be and you can go back to the data and you would have put this load will be on the x-axis and then this will be on the y. So the load them say go from 2 to 10. But if I go like this, 2, 4, 6, 8, and 10. Have I used up most of the graph?
No, sir.
No, sir.
No, so I'll actually lose a mark for the scale. So I don't want to lose any marks. So I'm going to remove it. And so how else could I do this? All right. Let's double it. So instead of putting every 1 centimeter, 2 unit, I can say every 1 centimeter is 1 unit. And that will lengthen it. And we have 2, 4, 6, 8, 10. How about this? Take up more space. Is it 3/4 of it? At least. All right. This is maybe they may accept this. They have on the mark scheme as a suitable scale. This might be the least that they'll accept, but I'm thinking we could go more. We could also turn the graph paper the other way as well and stretch it out some more. There are many possibilities with this one though, guys. So let me see if I can go on the safe side and leave it, because if I go 3 to 2, it's going to be hard to read. So let's leave it like this for now and see if we can get at least this side to have a better scale or a bigger scale. The length will go from 0.36 to 0.51. We have options here, guys. We can do something that is called breaking the axis. Anybody ever hear about breaking the axis?
Yes, sir.
Right.
Yes, sir.
All right, very good. So we can do that, as well as we can go the traditional route, which is to go by even numbers, and hopefully those numbers will be included. All right, so I suppose we could do like something like this. We could do 0.1. We could go 0.2.
Yes, sir. Yes, sir.
You're saying that, okay. We could go 0.3. We could go 0.4. And we'll go 0.5. And that will be easier for us to find. However, I'm thinking that this scale is still a bit small. It's small, but it's appropriate. Appropriate in the sense that the numbers them can find easy, and they are where they're supposed to be, but it's not. This is even half of the paper. Suppose in an exam situation, one thing they would probably do is take off a mark for the space here. But this graph could be bigger though. If it was me though, I probably would have turned the graph paper the other way. And make it look longer. But then I'm trying to do it very quickly tonight. So let's see here. All right. Anyway, just wanted to see what the graph going to look like this evening, really. So you're getting marks for these numbers being they are evenly spaced. You know, there's a scale there and the axes are labeled. So potentially 2 marks out of the 7 we get so far without even plotting the graph. And the next thing now is that we'll start to plot. We start to plot. So 2 will go to 0.36. And all right, so when the load is 2 will go 0.36. All right. The length is 0.36, 0.36. Well, this will be 0. Notice I could put zeros here, so in case persons are wondering what's happening. Put zeros behind it. No, you start to see what the numbers are saying. Here would be 0.35. That's halfway between 0.30 and 0.040. So 0.36 would be just that one box there above, and we'll put an X there. Everybody seeing that?
Yes, sir.
Okay. Yes, sir. All right, and then we have our 4.0 going to 0.35. So 4.0. All right, let's follow it then. 2.0, 4.0. Just for consistency, if the data say that 0.0 is there, we'll put it in our graph scale. All right, so 0.36 and then 0.35 for 4. And again, that looks to be some error. So that would be left out if at the graph in terms of if we're supposed to get a straight line, that one won't be included. So 0.35 would be right there. So far the graph, all right, we're not taking any shape just yet. All right, so the 6.0 now will go to 0.40. So this is an easy point to find. And we'll just put the X there. Graph looking towards that direction so far. And of course, what we have is 8.0 to 0.46. Now, of course, here is 0.45, halfway between 0.40 and 0.50. So 0.45, 0.46 will be the next box above it. And that will go with 8.0. All right. And so your graph is taking a certain shape at the moment. All right. Do we have any questions at this point? Everybody is seeing what's happening? Everybody understand what's happening?
Yes, sir.
All right. I want to move this. Yeah, you can move. All right. And then the X and Y business, yeah, kind of in the way. So I can just get rid of that. All right. So now, good. So we have one more point to plot, which is a 10. That will go to 0.51. And 0.51 is all the way over here. And it's up here. That's right about here. All right, guys. So this is it. Now, that's what the graph will look like so far. If these points are correct, you will get 2 marks. One for them being where they're supposed to be, and the other for using X as a plot. Right? Not dots, but X. So, remember that, using the X for the plot. All right. So far, this is actually 4 out of the 7 marks. And that's assuming that it's 1 mark you're getting for the scale and the axis. So the line now, I think they usually have a scale where them say if 1 point incorrect, you lose a mark. They usually give 3 for the plots, by the way. So probably they're marking it for each plot, in which case all the better. You're getting more marks for the plots and the line though than for what you did before. Let's just get the line in this. Instead of drawing a line, I'm just gonna line up it because we're going to use what we call a line of best fit here. Line gonna look like this, but remember now, we line of best fit should equally distribute the points that we have, and so far it's looking like this. Can we get it through one? Can we adjust this? Yeah, this looks better. Because we can start from the first point and then 2 points on either side of the line. So This is what the graph going to look like, guys. I believe just change the color to red. And that's the line of best fit. This is a line of best fit.
Excuse me, sir.
Yes.
Does the line of best fit have to start from the 0?
No, it doesn't have to start from 0.
So
This one didn't start from 0. It's a 0 all the way down here. We didn't start from it.
okay, sir.
Yeah.
Does it have to start on the y-axis, or can I start from a point like what you did?
Well, that's a good question. The graph, you see the line, you see this part of it, when you reach the stage of the graph, it's a personal thing. It's all up to you. You have options here. Students will plot the graph like this, and you probably get close to the full marks for that. But the reason why I wouldn't leave it like this is that the line of best fit is supposed to have, if all the points are not found on the line, then the point should be an equal size of the line. The same amount of points should be on either side of the line. So this line doesn't go through all of the points, but if there are two points outside on one side, then there must be 2 points left outside on the other side of the line, which in that case, instead of having 3 on one and 2 on the other, I say the better line of best fit. This is a better line here, because that way I have 2 on this side and 2 on this side. So hence this is the line of best fit. It is actually showing that it is fair. You know, it's not lean towards one side. You know, it goes between all of the points, so that's fine. Line of best fit is what we call that. All right. So that's it. This will work. If student plot from 0, let's see what will happen if a student decides to plot from 0. We could put the line there, and it's actually a good question to ask there. Student could actually draw this too, you know. There's some possibilities here. This will be accepted, you know. This could be accepted. So again, it's not like you must do it this way, but line of best fit supposed to have equal distribution. So 2 points on this side of the line and 2 points on the other side of the line. It go through this one. So that's also a line of best fit. So no, the marks are given for the line of best fit. So it doesn't matter where it's really start from, as long as it's a line of best fit. So I hope that answers your question, Daniel.
Yes, sir, it did. Thank you.
Yeah, you're welcome. All right. So yeah, that's it. So all right, if we leave it this way, I prefer it, but personally though, I'm thinking that this one is the one that follows the points would be more accurate. And I've seen students do questions similar to this, and they do it all kind of way, and they get the same answer. And I just say, well, you know what, it's a personal thing. Just follow the rule. Line of best fit, equally distribute the points, then you get your answer. But starting from 0 is a safe bet though. It's safe and easier to do, especially when the question were asked to find the gradient. So it's anything that works for you. I'm choosing accuracy over everything else. I'm choosing accuracy over ease. If I was gonna ease the route, I'll just use the line from 0, and then it would be so easy to find the line to actually find the gradient, which is what they're going to ask you for next. But this is how you'd approach getting the 7 marks, guys. That line of best fit, these points being correct, scale and axis there. Still thinking though the scale is a bit small. But again, we can fix that. In fact, this will be 0.05. So just to complete that. Yep. That's it. So different ways. This graph even look like I could go 4. I could go 4 to 0.12. And look like I had some options here. But this is just like a rough, like a rough sketch really of what answer going to be. All right. So it's good, guys. Graph work, first question. Even though they didn't specify that it will be the first question, but going back to those list of topics here, them said deformation is this, well, they put graph work and analysis of data, which is what we don't analyze anything yet, but graph work with deformation there is suggesting that the first question will be a Hooke's law graph like what we did a while ago. If we are to go back to that question, we plot this nice graph here. As a matter of fact, I probably would save this and send this in the group so that you can have it to look at afterwards. Remember that this is just a rough thing. It wasn't. You can still get a grade 1. All right. Let me see if I can how this would look. All right. And copy. Let's see how this is going to look in the group. This look awful. This look awful. You can't see it like that. When I do this, when I do that to it now, the graph paper just look. So, group everything. Now I want to copy it as a picture, but all right. Okay, see. The all right, a sample of the graph. This is just the graph work. We don't talk about the analysis yet. For and this will just help you to know if you them saying Hooke's law or the shape of the graph supposed to look. All right, and Hooke's law. And we put deformation in brackets so that you know what you guys want to look at. Deformation. Yep, hopefully that's spelled correctly. All right. And there it is. All right, so you should be seeing that in the group. All right. So all right, just to recap though, guys. So I told you about Hooke's law. All right, you should be able to state that law based on what I've showed you. All right. In fact, let's put the definition before. And the definition there are 4 ways or even more ways to define it, but I'm just showing you 4 ways in which you could get 2 marks to state Hooke's law. So I also learned that we can use this sign for proportionality. And let me just copy this as is. Group it, copy it, paste it, and it should be you in the group. All right. State Hooke's law. All right. All right. So that's in the group there, guys. All right. So and that's taking care of deformation. Gradient of the graph though that. All right, 4 marks for this. You don't want to play with these marks. This first question value 25 marks, guys. But the first 2 parts of the question, part A and part B, value 11 out of the 25. That's almost half of the 25 marks for doing the first two parts of the question. So you want to start this paper good, guys. You want to get a good start to this paper. Get the graph, be confident in yourself when you're doing the graph. Follow the instructions that I'm telling you now. Get your 7 marks or however many marks they give you. And go to the gradient. Now, to get the 4 marks of the gradient, you get 1 mark or probably 2 for saying what the gradient is. Anybody know what the formula for gradient is?
Raise over run.
Okay. Yeah, that's one of them. Or what?
Y2 minus
Y2.
Y1, Y1.
All right, so it would have been who's speaking there? Who was speaking? It was Giovanni? Shantae?
Sir, I was going to say the same thing that Benny just said.
Oh, okay. That's good. It's good, yeah. Which is actually correct. All right. I mean, all of these, you get 2 marks for this. Believe that, there's 2 marks. Well, probably 1, because I'm just seeing where they would have you get 1 mark for this. Because I just realized that they're going to give you 1 mark for the unit and 1 mark for the answer. All right. And I guess the answer and the unit, that's 2. Probably give you the other mark for putting in the right numbers here. But then that's depending on the graph there. 1 mark there though. You'd have to go back to the graph to find out what the gradient will be. We should be able to do that. We can actually come back to that in the interest of time though. But remember, guys, we said that the classes them, right now when get longer because we're getting near to exam and you guys need more time. Hope everybody is clear on that. All right. All right. So, what information about the spring does the gradient of the graph provide? All right. 1 mark. So we know Hooke's law already, but we didn't specifically tell you about Hooke's law or the Hooke's formula or Hooke's law's equation. So then from Hooke's law, you wanna say like this. From Hooke's law, the formula for Hooke's law is actually F is equal to K times X. All right. So this is what you're going to probably scribble somewhere though. This formula, if it's Hooke's law question, this is what you're going to use. You probably get 1 mark for having this drawn somewhere in the graph paper. All right. Hooke's law said that F is equal to you can say force or load that's measured in newtons is equal to the where you divide the extension to get something called, all right, extension measured in meters, by the way. You get something called, I'm going to write this in black. This is actually called the spring constant. All right, so that's the information they are talking about. Spring constant is measured in Newton per meter. So this is the answer. So any questions here, guys?
No, sir.
Sir, you could have used E instead of X, don't it?
Yeah, you can use, and I wouldn't call that E. It's not. It's a Greek letter and I'm use. No, epsilon them call it.
I think so.
Yeah. So if you get that version of the law, that's how them teach it in the US sometimes. So some teachers will use that. So yeah, that's okay. That's okay. The information that is provided by this, according to the question is the spring constant. So the gradient provided. All right, this is spring constant. So from Hooke's law, F equals Kx, you're going to say K, because you did actually plot. And why is it going to be K? Is that you plotted, if you plot force against extension, it's actually the same thing as, you're going to say something like, therefore, like force divided by extension is equal to K, which is the spring constant. So, I mean, if you write this on the paper, you're going to get the 1 mark. They're looking for the keyword, which is spring constant. All right, so when you plot a graph of Hooke's law, the gradient gives you the spring constant of the graph. What the spring constant is as a number or a value that tells you how strong, or you could say, or how rigid the spring is. All right, so the higher the spring constant from your results is the more rigid the spring is. So this is very useful. Like, for example, if you're gonna build a car, you know that you're going to need a very rigid spring. You don't want a spring that keep doing it unless you want those hydraulic cars that like the rappers them having some of them videos, are some pimp or someone want to show off to some people on the roadside. But we want so the spring constant tells you how rigid it is. So that's what the spring constant is. Just in case I ask you what does the spring constant mean, yeah, so you measure how rigid the spring is. But from the graph, where you find the gradient of a Hooke's law graph, it's going to be the spring constant. All right, and that's it. So yeah, and then this is where the analysis part come in, guys. Use the graph to find the original length of the spring. All right, maybe this one might be the last thing I'll show you before I leave, because I want you to get this concept. I don't want you to teach you too much of a new topic when you're just learning it. So I'm gonna basically this be like one of the last things I'll show you. All right, the original length. When you plot these graphs, it's a dotted line you use to carry it back. So what we're going to do here, I'm gonna you use dotted lines to carry it back, but because my hand might not be so straight, I'm gonna take a line from here and I'm going to continue. So what I would do here is just draw some dotted line. That's what you would do in exam. Let's start back, because the original length of the spring is like starting from there. So yes, this is why Daniel was asking the question. You remember he was asking if you should start from 0. If you had started from 0, that's why I say I'll choose accuracy over ease. It would be easier to find the gradient if I started from 0, and then the line would be nice and straight, and I could find and easily find the gradient. However, for accuracy, where they ask you to find the original length of the spring, this now is it. This is it. You get mark here, original length. So that's why I recommend starting from the first point in this case. And to save it's a more accurate thing to do then. May not be the prettiest graph because it don't go through everything and the students like a perfect graph, but it gets the answer that CXC is looking for. Remember, not really looking for a perfect graph, they're looking for an accurate graph more than. So original length, guys, is carrying the graph back to the y-axis, back to where it started. In fact, we would call this the y-intercept for those of you who are math savvy. And the original length would be somewhere here. As a matter of fact, we could find it. It's 0.30123. So it's actually going to be 0. Very good. 0.33 meters. So that's it. That's the original length of the spring. So No, if I do it on the graph, the CXC will give you the marks there, but you get 2 marks for that. Dotted lines 1 mark, and then the answer 2 marks. So so you're going to say like C graph paper. Graph them, go and look at it, 1 mark there, and of course the answer 0.33, that's the 2 marks, so 0.33 meters. Oh, and then they just actually here, but then this not can. So we're almost done. All right. Use a gradient to calculate the extension of the spring. Again, you see that formula that I showed you there? That's key here. 6 marks though. The reason why this is 6 marks. There's a little trap them set for you here. Gradient, use a gradient to calculate the extension of the spring if a 7 kilogram mass hangs freely from the end of the spring. Hence, calculate the length of the spring with the mass attached. All right, 6 marks. So guess what? Them have extension. When they have extension, they must have load. You get, for the 6 marks, this is 1 mark. 1 mark for Hooke's law. They just write the same thing I wrote before. Force extension. Force divided by extension is equal to spring constant. All right, 1 mark for this formula. The next mark now, they have, but it's because they don't give you the force or the load. You have to go back to basics here. You have to convert the mass to force. And there's another formula used to do that. You're gonna say well, you're gonna say force is the same thing as weight. So all right, so convert mass to force by saying weight or force is equal to mass times gravity. Well, I think they put the G here. This G, which is 10, will be used here. Will come right here. So there you go. So this 10, and we'll just put in the numbers then. And this question doesn't have to be hard, guys. I mean, this is, bread and butter here. This can be done. But you 10 there, the mass, they give you 0.7. Why we're using it is that every time we say mass, and we know that it's Hooke's law, the mass must be converted into newtons. The only way to convert mass in kilograms to newtons is by multiplying the mass by the gravity, which is 10 in this case. So 0.7 times 10 will give you 7 newtons. All right, you get the 7 newtons, and we will input. And we put the 7 newtons. Everybody seeing what we do here?
Yes, sir.
Remember the mass does not have weight. The mass only have weight when gravity acts on it. And so to do that, we multiply the mass that we have by the gravity. That gives us the weight. The weight now will become the load or the force that is placed on the spring. All right. And then the gradient that we found will be the spring constant. So we'd have to find the gradient of the graph. They ask to calculate the length of the spring. So this is what they're asking for the extension. This force is 0.7. This spring constant is the gradient of the graph. So once we find the gradient, we drop that in, we get the extension, bam, we get with 6 marks. End of discussion. So this question is as we say, it's very doable. And they ask here, if the spring is stretched beyond its elastic limit, how will it affect the shape of the graph? So if we go back to what I showed you before, they wanted to know if you know about the tail of the graph when it disobeys Hooke's law. You see that? The shape of the graph is affected here. So it start bend towards the, well, just start bend away, really. It's start a bend or tail at the end. All right, just like what happened when Pinocchio stopped telling the truth, right? What happened to Pinocchio?
Nose get longer.
Exactly. Right, good. So his nose started to disobey Hooke's law, if you want to put it in that sense. All right. So how would you identify the region where the proportionality exists? I just say shaded portion. All right. Shaded portion of graph below straight line. Yeah, so that's the identifier. 2 marks of that shaded portion of graph below the straight line. Yeah, part of graph. All right, so that is it. 2 marks there. All right, classify each quantity. They want you to know what is scale and what is vector. 2 marks. I'm just run out a question to ask you. Sure. All right. Well, load is a force. All forces are vectors. So that definitely would be a vector. Extension is meters. That's length. Length is a scalar. 2 marks there. All right. So that's it. That's pretty much it. In 2013, this was it was a relatively easy question, relatively. But the results in 2013 weren't that great, really. So hope you guys don't fall into the same trap. Those students did not have the topics that you have. And they didn't probably get the understanding like you're getting it now. So going back to it. So all of that was showing you there's deformation, guys. All right. So should I was it sent in the group, the list of topics? Maybe should send this. You want all of this in the group, guys?
Yes, sir.
All right. Let me just group in it that and send it. All right, so it should be there. Oops. All right. Come in again. So copy and paste. All right. All right. So the parts highlighted the parts in red were done in class. All right. Please see notes. Oh, yeah. All right, so there you go. We have that there. All right, so that's there. And then now, the next thing now are turning forces, but I mean, I don't know. See that for another time. And remember, we're just sticking to Hooke's law tonight. And this will be the next question when we look at the Hooke's law. The turning force is part of it. All of these questions here that they have asked before. So we're going to have a look at this next class. Question back in 2017. All right. So going through the papers, finding what looks like the topics that they're saying. And I think this is it. We have everything here. All right. You don't need that still because all right. Yep, that's it. So we'll cover that, guys. All right. We'll cover that. So that's it. No. So guys, how are you feeling after tonight, after class tonight now? Did you learn anything?
Yes, sir.
Yes,
Yes,
sir.
sir.
All right. Hope so. I'd love to see that you learned something. So, as I say, if I find any more hooks law question and when I put out all the steps here, it may not be CXE. It could come from even other exam bodies like GCE that's close to CXE. I know they set questions on that. So, just in case CXE want to get creative, which they can be, they might just borrow questions from GCE. And so we're going to be hunting those and see if I can put together a little thing, booklet or something where those questions come in. But keeping it simple though, guys, as we say, less is more. No, as we say, remember what Hooke's law state, right? Remember what the graph supposed to look like. And of course, remember the rules when you're plotting your graph, what they're looking for as well. All right, those are the summary of my instructions to you guys concerning that. All right, and so that's it. All right, now today's just Tuesday, so we have class again Thursday. All right, we're going to try and cover turning forces, which has to do with moments. So you can read up on moments, which is what they will likely ask you about. Moment of a force, most likely asking you to define the term moment of a force, and also the two conditions that are required for an object to be stable. Very popular questions asked there. And we see a couple past questions. There are quite a few questions on turning forces through CXE, so we can have a look at those. Some of them can be really tricky, but we're gonna look at the basic ones and work our way up from those. All right, that will take care of and when I'm speaking to you now, I'm actually looking at the topics that I would have sent to here. That's topic 3. Yeah, we're going to focus on that next class. And as I said, the ones that are highlighted are done in class already, so you have to check your notes for that. 11 to 15 are major topics. I think we should meet maybe I'm saying on a Saturday we should meet. We have to do this. Alternating current resistance, magnetic forces, electromagnetic force, and motors. That those can, the students get in trouble with these a lot in exams. All right, so we want to spend time on this one. All right. So that's it, guys. So as we say, as a matter of fact, you know what I do? I'm going to send this for you guys to work on. You have the answer for me. This is what I'm going to send. All right, try and get 6 marks by yourself. All right, so I'm going to put the instructions here. Try this question. All right. Before Thursday. So, all right, you guys have to go. This is when you probably can take a book or take up your book or try and read something, but you have to read a lot for this one. And Thursday would be, I think, May 13. All right. All right. All right. Go on research. All right. Ask questions in the group. Right attitude you need to pass this exam. All right. Ask questions in the group. Yeah. All right. and discuss in the group. Yeah. So that's it here. So these are my instructions to you guys. All right. All right, so all right, so let's finish this now. All right, so yeah. All right, so that's done. All right, so I'm saying, guys, one day at a time. All right, you have to do your part though. You know, at this stage, you should spend about 15 minutes to half an hour revising one of those topics that you see on the paper. 18 of them. 18 of them, but we have to be sensible about how we tackle them. It's not an essay and it's not 18 essays you need to be writing on each of these topics. It is just the basic stuff on each topic. Because remember, it's an exam. The exam have a limited time, so them can't ask everything, but they'll ask very specific things. Those specific things is usually to define or to explain or to state. All right. Those are the three keywords when they're asking questions. Define, explain, state, suggest. Yeah, maybe suggest why. Those are questions, as we say, you're focusing on. Right? Not the essays in textbook and so them right, because these people tend to get very panicky and not keeping them cool when these things happen. So take the topics, calm yourself, spend half an hour on each topic per day. Sufficient break between each topic is recommended. You don't want to crowd your head with too much information. So that is the plan, guys. All right. You can get there. So just believe in yourself and follow the plan. All right. Follow the plan that I'm communicating to you. And I say, if you have any questions, you text, in the group and start discussing the material or the work, whatever I send. All right, guys. So thanks for coming out this evening and enjoy the rest of your evening and stay safe. Yes, sir.
Yes, sir.
Yes, sir.
All right.
Bye, sir.
Yeah, bye.